welcome to today's class. Today we are going to be doing an introduction to the periodic table. I, Kylie Gomez, and my other peers, Devin Jordan and Sky Celeste, will be discussing today's how to use the periodic table properly. With this in mind, we'll be going over the atomic number, the symbol, and the atomic weight. After that, we are going to differentiate between an element, a compound, and a mixture.
Our first slide is about Dmitry Mendeleev. He was born in 1834 in Russia and grew up to be a chemist. He's passionate about chemistry, which led him to the discovery of the periodic law. He also created the periodic table itself. He predicted the properties of the elements yet to be discovered. He determined the dependence between the properties of the atomic weights and of the elements.
So, what is the periodic table, you might ask? The periodic table shows all known elements in the universe. With this in mind, remember that not all elements in the universe have been found. So there's elements out there that may have not yet been discovered. Yes, the periodic table also organizes the elements by chemical properties, starting with noble gases on the left, metals on the left and noble gases on the right.
Next up, we have how to read the periodic table. So, let's start by drawing our example. We are going to use the element carbon. There's a lot of information on this square, so let's go ahead and break it down. Up top, we have the atomic number. Then we have its symbol, followed by the name of the element, and finally, its atomic weight. Later on, we're going to go ahead and see how these two concepts correlate.
Okay, what is the atomic number? The atomic number is the number on top, using our example of carbon. The atomic number shows the number of protons in the nucleus of an atom. It determines the chemical properties of an element and its place on the periodic table. The atomic number identifies a chemical element. In an uncharged atom, the atomic number is also equal to the number of electrons.
Now we're going to discuss what is the symbol. So a symbol is an abbreviation of the actual element name, and in this instance, it's carbon. So a symbol is actually very important in the instance that it can be used on an everyday basis. A symbol is used for scientists and all individuals so that helps them find the element quicker. It also helps when you're using it when you are mixing/combining other elements. So an example of this is when you're mixing sodium chloride. In this instance, you would use your abbreviations Na for sodium and Cl for chloride to prove this mixture. And it's also helpful when you are making equations.
And lastly, we're going to go ahead and look at what is the atomic weight. So continuing on with carbon, we have the atomic weight is just 12.01. The number of protons and neutrons in the nucleus of an atom are what define an atomic weight. Typically, you will always see that the atomic number is doubled, and that will somehow relate to our atomic weight total.
All right, so moving on. How do I find the number of protons, electrons, and neutrons in an element using the periodic table? So first, the number of protons is determined by the atomic number. Second, the number of electrons is determined by the atomic number as well. And then lastly, the number of neutrons is determined by the atomic weight and the atomic number. So it uses both.
Next, we have a short video that helps you better understand what our next part of the discussion is, which is the difference between an element, a compound, and a mixture. Now we are going to watch a short video that helps you better understand the difference between an element, compound, and mixture before we decide to discuss it with you.
It's 101. Today we are talking chemistry, and this is one of my most requested videos, the difference between elements, compounds, and mixtures. Let's get started. Everything around us is made up of atoms, and there are 118 different types of atoms that we call the elements, and you can represent all of the elements on a big table, which we call the periodic table of elements. Each element has its own set of characteristics, so it might be quite a small atom, it might be a large atom, it might be a metal or a non-metal, it might like to react easily with things, it might not like reacting with things. And so based on its position within the periodic table, we can actually determine a fair bit about that element. For example, all of the metals tend to be grouped together, and all the non-metals tend to be grouped together. Each element has its own preference for how it likes to bond with other atoms. For example, we have our 7 noble gases: helium, argon, krypton, radon, xenon, organesson, and neon. And these guys like to hang out as just individual atoms. They don't like bonding with other atoms from other elements, or even other atoms from the same element. They like hanging out on their own, so we call them monatomic. Mono meaning one, monatomic meaning single atoms. Some elements prefer to hang out as a pair or as a cluster of the same type of atom, and we call these molecular elements because a molecule is when you have 2 or more atoms stuck together. So for example, hydrogen likes to hang out as a pair of hydrogen atoms, so we call that a molecular element. Nitrogen, oxygen, and chlorine also like to form pairs, so they are also molecular elements. Our third type of atomic arrangement applies to 80% of our elements, our metals, and that's this 3-dimensional shape that we call a lattice. And they don't all form cubes like this, so they form other different 3-dimensional shapes, but in all cases we call it a lattice. When you have 2 or more elements bonding together, we get what's called a compound, and these can be in the form of a molecule or a lattice. Water is an example of a molecular compound because it forms molecules, and each molecule of water contains 2 hydrogen atoms for every 1 oxygen atom. Carbon dioxide is another example of a molecular compound because it forms molecules that contain 2 oxygen atoms bonded to every 1 carbon atom. And this is how we get the names carbon dioxide and H2O. We can also have compound lattices. So salt, for example, is sodium chloride, and sand is silicon dioxide, and both of these compounds tend to form these 3D crystal lattice structures. Lastly, we have mixtures, and mixtures contain a whole bunch of different elements and compounds, and we don't necessarily know the proportions of the elements within a mixture, unlike in a compound where we know exactly what the proportions of the elements are. And for this reason, we can't give a chemical formula for a mixture because we don't actually know the proportions of the elements. For example, if we had a bottle of pure distilled water, we can label it as H2O. In that bottle of water, there are 2 hydrogen atoms for every 1 atom of oxygen. We can't write a chemical formula for tap water though because it's a mixture. It contains water molecules, but it also contains chlorine, fluoride, nitrates, phosphates, and a whole bunch of other elements that we might not even be aware of. So we can't actually label that H2O because it's a mixture of all different elements and compounds. And that's the end of today's lesson. We've covered elements, which are different types of atoms. We've covered compounds, which are made of 2 or more different elements bonded together. And mixtures contain a variety of compounds and elements. Thanks for watching, and I'll see you next time.